Hi everyone, my name is Philip from DHI. I'm the business owner from Mike Shi and Mike Plus Rivers, and today I'm happy to give you a webinar on how to use the water balance calculation tool. That is kind of an add-on tool for Mike Shi to evaluate all the water balance items that you simulated in your calibration in your simulation. The meeting will be recorded. You can request the recorded meeting afterwards. We will also share the presentation with you. And this time we will also, like in the first webinar, share with you even some templates that we prepared ourselves in Excel and over the past years for our projects, which you can then leverage for your projects. I have prepared a presentation today. We will start with that, but I will pretty soon move directly to a hands-on practical live demonstration because it's way easier to show you all the necessary steps that can be done with this water balance tool. I would really like to encourage you already in the beginning and emphasize the benefit for you to use this water balance tool. At least the most simple applications that I will show you in the beginning. And then you will probably anyway would like to use the more advanced stuff that I will show you in the middle. At the end, I will leave this time a little bit more time at the end, free for discussions and questions, because I can think that you have maybe some ideas already how you could use the water balance tool for your purposes, and I'm more than happy to directly answer them today. If you have ideas afterwards, feel free to reach out to me via email, and I think we can start. So today, as I said, we will go through the water balance tool in Mike Shi. My agenda for today is why you should use the water balance tool, and there are good reasons for it. Then I will go with you through the basic functionality and the introduction. Also a short excursus how to leverage the water balance tool for debugging, how to customize your own calculations, which is even possible, and a new thing, how to combine the water balance tool with the auto calibration tool. And at the end, as I said, we have time for questions and answers. So why should you use the water balance tool? Maybe you have seen sometimes such kind of graphs, which is obviously a simulated water level, probably in a river, which has some severe instabilities. If you are lucky, you had such a detailed river time series and you see the problem, but sometimes you are not able to see the problem and the simulation runs through quite smoothly. Then you can do this thing. This is the so-called chart output of the water balance for a Mike Shi model. And what you can see here is, there you can always see the total error. So it always sums up all water balance items for the whole simulation, and it shows you the total error. It also shows you the fluxes, which can sometimes be quite high. But after each run, after, let's say, constructing a model from scratch or going into the calibration or while the calibration process itself, it's always worth to create this chart output from time to time and check if your total error is, I would say, less than 10%. This chart output is actually a separate executable, which I will show you, that reads a certain text output, which you can also change and modify yourself, which I will show you later. So if we start with the most simple example, you can see here, this is the Carob example that is pre-installed with the installation in the default root folder directory. So whenever you want to use the water balance tool, it is essentially required that you check here storing of water balance. If you do not check that, not everything is created in the gridded results. But if you check it, you will see some of these things are checked or forced to be checked and grayed out, because these are the items that are required to calculate the water balance afterwards. So in this case, I have set for the very beginning it to 1 year. And then in order to create a water balance tool, I would create a new file here. And if you go here to the subcategory of Mike Shi, next to the Shi folder, Shi file, you have the water balance calculation tool. I would create a new empty file, and then it already guides you. It wants to have the flow result catalog file of your model. So for example, I have here my model, I have ran it already yesterday for 1 year. And here, all the outputs that you have probably seen many times are already there. And what you need is the summarise file. It's a so-called result file, and it tells the water balance file which item is created or stored. So in this case, I copy the link here. I go to the result files folder, select this summarise file. Then you have already several options. The easiest thing, especially for this chart output, is to do the full catchment water balance. That means it calculates the water balance for the whole active model domain. You could also do it for subcatchments. If you have maybe 4 or 5 subcatchments or a focus area or a certain soil type or hydrogeological unit that you want to evaluate in detail, then you can provide the water balance tool with a DFS2 or even a shapefile that goes along with an integer grid code like 1, 2, 3 for each subcatchment or each soil type, and create water balances for each soil type. So in this case, we would go for the full catchment, and you can do then an approach that is called the resolution type is the full area. So it would create, for example, for the whole catchment one time series, or you can even go to single cell. Then the outputs would be DFS2 grids. Then you can step through the time steps and see the spatial variation also over time. But as I said, the most simple thing is catchment area. Then it says the post-processing text is not valid. You have here at the top 3 buttons. And this will now extract, you have to save it. In this case, we normally have for each model file, if you saw how to create a MikeShe model 1, we normally have this analysis folder, which enables us to sort out a little bit and standardize the evaluation. And we all normally have a WBL folder. So here you can see I have already an example prepared. So I create a new one called 2. Then it directly asks me to execute it for this simple model, and especially because here the type area is chosen, it runs quite fast. So now the so-called water balance gross files are created. You will see them here, which are binary files that are relevant or required for the water balance tool to run. And then you can go here to the second tab, the post-processings. You can create here only one, but of course you could create here as many post-processing tools as you want. Depending on if you want to do this for one catchment or several subcatchments, of course, you maybe need more than one water balance file. Also, if you want to do it area-wise or for each single cell, you would need to distinguish this between different files. So in this case, as I said, the easiest way to start is one item here. I already call it here chart total WBL. I say here use the default configuration file. How to change that and individualize that I will show you later. And then here you have the drop down. I know that it's not used as much as it could because it looks a little bit difficult. I must say the documentation on that part is quite good. I will also show you in a minute. So this meeting today is really to lower the resistance or the entry barrier for you to start with that. Again, you have here the total water balance, which we use in nearly every project all the time. You also have here your error of each component and many items. You can also make the water balance for each groundwater layer if you have a full 3D groundwater model for each layer. You always have the option to have a kind of lumped water balance or a more detailed for the experts. But what we do now, we go for the chart output total water balance. Then it asks you if you want to evaluate really the full period. You could also change that and make it for a sub period, for example, to exclude a hot start period if you were using a hot start file. You could also change this from accumulated to incremental if it would not be that the item. For example, if I would like to go for a total water balance, You can also say, do you want to use the default output time step? In this case, I used here 24 hours time step. That's why I can see here the 24 hours. You could do this incremental. So it would take always every 24 hours the accumulated water balance for each item. Or you can do it accumulated. So you would have the full amount at the end of the simulation. And you can produce, if you have this area-wise approach, a table, which is a TXT file, or a time series file, which would be a DFS0 file. If we go for the simplest one, which is the chart output, I'm not asked because it needs a text file to be read. So here I create a new one. So I have defined that. And then depending if you have here several or only one post-processing, you can say here, run only the selected or run all post-processings. In this case, it doesn't matter because I have only one. So it's done. And under the result, you would have now, again, for each post-processing process, one tool. And if you go here, click open, it will open this chart output. It's a very outdated comic, graphical image kind of. We are working on that to update it. But at least I must say it always fulfills the purpose. It gives you a very quick view what is happening in your catchment. So around 900 millimeters of rain, 560 is evaporating, a little bit of boundary flow. There is no infiltration from the river to the groundwater, but 150 millimeters per year are flowing from the groundwater as base flow to the river. We have 161 overland flow, a little bit of storage change in the overland flow, unsaturated zone and in the saturated zone. 379 millimeters are infiltrating, but 185 are already exfiltrating or evaporating again with the capillary rise. And we have a little bit of saturated zone drainage to river. This image adapts depending on which modules you activated. You could also use this tool in a way that you open a different text file that is formatted exactly the same way. Then you would get a different water balance. For example, here I ran one for 3 years. That's already the changed one, doesn't matter. So then the values would change. In this case, I even attach this file to my taskbar at the bottom. You can find this tool yourself in the root folder. And you can start it even here. You see it independently of MikeShe if you want, and create the water balance chart output as you want. The next thing you could do is here the PFS file. So when you install MikeShe, you have here this default configuration file. Remember that because here you get a copy. You could make now a copy in this case. Go to a folder where you are pre-processing your model. I recommend to put the config file always next where you're using your water balance file, and then modify that. We will do that later. Once you have created such a water balance file, I closed it. You have the option to even attach that. So if you go to post-processing under simulation statistics, you can enable here one or several water balance files and attach them to your SHE file. That means you need to prepare this file only one time. And if you make a copy of the model for another scenario or for another calibration iteration, everything will be executed completely automatic. That means you do not have to do anything again, manual work. So what you can do then here, open this chart output from here. So it's really for you, once it's prepared one time, it's really no effort for you. And it can prevent you also for running in the wrong direction within your calibration to see if the total error is starting to increase, then you maybe changed something by mistake and you can go back your proceeded steps kind of. So another example is, now let's assume, like I said, I want to run another scenario. You open the model again. And in theory, you would now change something, for example, the period of time, or you change some modifications, you click run. You have, again, as I said, the same file, and once it's run, the water balance file will be executed at the end of the simulation, and you can open the results directly yourself again. So this is really the minimum you should use the water balance tool. It's not much effort. You only need to set it up one time, and it enables you to track the error of your simulation quite easy. So we went through the steps, how to use that. Yeah, maybe worth showing you the documentation quickly. So here, the links will be part of the presentation that we share. And here, exactly this chapter 6, you would find it here under Getting Started, Results, Water Balance. You find here everything in a good way documented, what you need to do, what you can do, how to extract it, how it works. Exactly the steps that I went with you through right now. You can also calculate water balances in batch mode or from the command line. And what is important for you, especially if you would like to configure yourself individualized water balance items, you have here a table. You have here a good explanation of how the already implemented water balance items in this default config file, PFS, are grouped. But you have here a good explanation of all the single items. And this is what you would need if you would like to individualize here the water balance stuff. Now, another example is, as I said, for example, you would like to use here subcatchments. I pull up here another example, which was one model here that we had in North Germany, which looked like that. You can see it here a little bit here. This is the higher topography. We have here some lakes in there. And you can see the water was flowing here from north to south. Here we have a watershed divide by the river. But you can already see a little bit that we have more or less several subcatchments. We have here one head or top catchment, one center catchment, and one to the east and one to the west. So what you can do now, for example, you can, where is it? Create, based on your active model domain, an integer grid code DFS2 and assign one grid code. Here is a 1, here is a 2, here is a 3, here's a 4 for each subcatchment. And then create one water balance file. Again, I select here the shearers file. I change here to subcatchment, again area. And then I provide it here with this DFS2 grid I showed you. And then you can have several items processed in one file. So for example, subcatchment 1, 2, 3, 4. For all of them, I needed for my report the total water balance incremental. Then you go here for the total water balance, change it to incremental, say grid code 1. If I want to have exactly the same thing for subcatchment 2, I change here the grid code 2. Of course, you need to consider here a reasonable naming to not get confused. And for each subcatchment, I created this chart output. I created the overland flow balance, the unsaturated zone balance. For the saturated zone, I wanted to have the detailed one. And this I did for each subcatchment. If you are, let's say, experienced, you could even think about creating this for one subcatchment and then editing the water balance file with the text editor. But there you should always do for sure a safety copy. But in theory, you could then copy paste one block of text, change the subcatchment from 1 to 2, and then easily implement it. So it's up to you if you would prefer to work in the text editor or if you do this in the graphical user interface. In this case, I show you something else, kind of extraction from our report. So this water balance tool enables you really, sorry that it's German, to lump together the very complex and physical-based cell-wise results that you produced. So in this case, you can make, for example, these column diagrams. Here, precipitation is blue, evapotranspiration is yellow. So we normally use intuitive colors. Then you have dark and yellow-green groundwater inflow and outflow, direct runoff, brown groundwater going to rivers, rivers going to groundwater, and a change in the groundwater storage, which is also very interesting. And we did that now for every subcatchment. We lumped them together as summarized values for climate, groundwater, and rivers, because this was requested by the authority, our main client. You can also make these cake diagrams kind of where you get a better feeling of how much water is coming in and out from which water balance component. And you can do this for each catchment and combine a little bit how the water cycle is happening in each subcatchment and how they are communicating with each other. Another thing what you can use it for is, if I go back to my example, let's say it's not here. I created now exactly for this model, I've showed you the chart output. In this case, it's not a very good example because it's very good optimized already. The model, the total error is only -1, but at least you see a significant total error and you would like to investigate more where it happens. Another thing that you can do, and I would recommend again to do it for the whole catchment, for the whole active model domain, you create another post-processing and you choose the item error of each component. It can be a time series file or a DFS0, doesn't matter. Then you run it again. I will not do it again now because I have it already. You always have here a kind of preview, but it's not only one time series. What you will get then, you will receive for each time step the error of each component. And this clearly shows you already in which module your error is happening. So what I normally do then, I must say, I plot it here, or copy paste it into Excel. I see here a soil moisture error. This is the canopy interception error, overland flow error, overland flow drainage error, unsaturated zone error, saturated zone error, and total error. And if I look at the chart now, I normally go then here to the first diagram. And then I change quickly the color from the main items to identify which one it is. And I see here, there is the purple error term, whatever it is. This is my problematic one. And it's balanced out balanced out a little bit by the other terms. But obviously here, and it is pretty often the case, the main issue is within the unsaturated zone. So I see here, that's the green one. So now I know already, I do not know where in terms of the DFS2 grid or location within my model the error is happening, but I know in which module. And then the next step would be to set up a new water balance file. Here, I select again the shearers file. I go for the full catchment, but now I choose the single cell approach. This runs a little bit longer. It can take, depending on your model simulation, 1 hour or longer. So makes sense to sometimes start this at the evening, overnight. And once you have accomplished the error of each component and you already know in which component you need to look into, You can now create map output. You could also do it for the total error, but you can also directly go into the single components, overland flow, and so on. And I created now the unsaturated zone error. Here. Yeah. Again, what it does, it creates a transient DFS2 grid, which shows you the error in each cell. I think I can open it here. Yeah. So I changed now already the coloring. Yeah, one more comment. You could do this error, of course, incremental, but it makes way more sense to do accumulated one because you will get a transient output. And if you have this transient output, I go to the beginning. This is how it looks like in the very beginning. You could now step through all the time steps, but at the top bar, tools, navigation, you can directly jump to the last time step and see directly where the problem happens. So in this case, I have single cells where I have a pretty large error. If I hover with my cursor over the single cell in this blue part here at the bottom, you can see then the value, which is here minus 2000, while the rest normally varies between more or less than plus minus 1. Now in this case, I know the model quite good. I know already what the problem is. I can show you in a second. But you could also go now into the single cells and look which soil type do you have defined, or maybe the unsaturated zone parameters not chosen properly. In this case, I look at the head elevation in the saturated zone. This is a full 3D groundwater model. And I make a cross section through the problematic area here. I make a profile plot for the head elevation and the 3D calculation layers. You see here now, if I start the animation, the red is the head elevation of the top layer. The green is the head or pressure head in the second layer. I already see here a little bit of problems. You cannot recognize what the problem is here at the moment, but if I go to the last time step, my problem is that the first layer is running dry. And as you may know, Microsoft does not like that. So the option here would be to adjust a little bit the hydrogeological bottom of the first layer so that it does not run dry. And then I would probably get rid of this unsaturated zone errors because the error happens probably in the unsaturated zone, saturated zone coupling. This normally also helps you a lot in the plausibility of the results, not only for the water balance, but it also speeds up your simulation if you fix these issues. So if you have, for example, also issues with a very long simulation time, which is also quite common, I recommend you to go this, check the chart output, then check the error of each component as a time series, identify the problematic module, and go for the map output for exactly this component. So this is a good way how you can leverage the water balance tool also for debugging your model. What I told you, I have put here the slides for later reference. This is normally what you would see without adapting the colors. As I've shown you in, I think, the first how to build a Mike model session, I always work with these default color palettes, which simplify my life a lot and make it way more easy. So together with my team, Max and Sultan and others, we have created a bunch of color palettes that we can easily use for all these purposes. And turning this into different colors, you can already see that what is the problem. So you take, again, the largest error term for the map output in an accumulated way, jump to the last time step, change a little bit the coloring, and you can quickly identify where you have problems in your model. Now, how to customize your own calculations. This is maybe the more advanced stuff. I have put in the PPT the links that are relevant for you. So what you can see is the list I have shown you some minutes ago is the available water balance items. So I go again to the website. The naming is sometimes not a little bit straightforward, so that's why I recommend you to go into these tables. And what you can see, actually, MikeG is calculating a lot internally. You normally don't see that, and you also cannot see everything in the gridded output per default. So if you go into your MikeG graphical user interface inside your model, you can see already many grids that are produced per default. But some of the items that are calculated internally are not per default created as a DFS2, but you can create them if you want yourself. So the workflow would be you make a copy of this PFS file, which I did some minutes ago. Rename it. Don't change the one in the default directory. That could lead to confusions. And then you can edit this PFS file in the text editor yourself. And whenever you want to change something, you need to create such a block. This is one item. I copy it now here, for example. And whenever you create a new one, count this up. So like +1. So if I would now like to create one more item, I change this from 35 to 36. I paste this new block. And what we pretty often do, we pretty often use MikeG to assess a very sophisticated recharge, groundwater recharge. But this is per default not part of the total water balance, since the recharge is an internal flux. If you use the water balance like it is defined here, it will sum up to 0. But we normally tweak this a little bit. You can change the title and say, including recharge. In this case, I think the total recharge to groundwater is even part of here, a different item. So I take here the recharge, go up, and add here this group. Save it. And if I go now to an exemplary water balance file, I need to go to the middle ribbon for the post-processing, click at the top to the processings, and I uncheck. So it was checked. And now I go to the use default config. I navigate to the one I created now, which is this test one, open. And if I go now here to the very top, you can see here water balance, total water balance, including recharge. Now what we do pretty often, we produce this total water balance for the whole catchment as time series, and then we use Excel templates. So I will make now a short demo what we do, but this is rather inspiration than a full tutorial because you can modify that your own. Let me check if I can go for the default one. So let's say I would like to create now the total water balance, but not as chart. I would use this first item. I take incremental in this case. I choose table because this matches better with my workflow. I think this runs quite fast. Yeah. And then it looks like that. Is it a text file? Yes. And what we normally do, We have a very extensive Excel sheet. And this starts with an import sheet. In this case, we have a German date formatting, so this could be also very different for your country. But what we do, we delete all these columns, and I copy all these items here, like that. Then it automatically creates here a real date, because this is how it looks like in the text output. And then we have here a pivot table that is referring to these columns. So we can refresh them. And I will get now an adapted list of water managed years that I would like to evaluate. Here are several evaluations working automatically. And if it works now, yes, it's not perfect. But then we have several charts that are automatically updated. So exactly the new results. So in this case, it's not perfectly prepared, but let me go one step back. This is how it would look like. I'm happy to share these with you, because this is normally how we start with the total water balance in a more detailed way. So you can have here different methods how to visualize it. We pretty often go for this bar approach, where you have in blue the precipitation, then you have in orange the evapotranspiration and recharge. So this is like the basic climatic water balance that you can use. There are different methods to visualize it. And you can do also very nice things, for example, only for the groundwater balance. So here you have, in this case, in this model, only one big positive component, which is the recharge, which ends up in drainage outflow. You have wells that are pumping the groundwater. You have base flow, which is discharging into the rivers. And of course, you have then, in this case, if the three negative terms are less than the green positive recharge, you have here a groundwater storage that is filling up. In the next year, maybe the recharge is less and the outflows are exceeding the inflow, then you have a negative one. And in this case, you can also nicely visualize here for your clients or for your partners or even for yourself the development of the groundwater storage over years. So in this case here in northern Germany, we had very dry years in 1819. And you can see here how the groundwater storage was deplenished over time. You can even combine, of course, this with a second sheet where you have a scenario run, and you can create differences for each other and even evaluate them then here in a table view. For example, here we have two scenarios. One was without irrigation for the agriculture in the reference run, and then we turned off the irrigation and we wanted to see how it changes the recharge, how it changes the ET, and how it changes the precipitation. So we will not go through that in detail, just as an inspiration what you can do. Another thing I would like to share with you, at the moment it's not yet implemented, but we plan to do that in the near future. That is, no, let me go one step back. Regarding the configuration of this PFS file. What we also did, we had one client here in northern Germany where we wanted to see the recharge, including the river influence and excluding the river influence. So if you remember the formula, the equation I have, sorry for the jumping, let me check here again, this one, the second one, yeah. You see here the total recharge to saturated zone, which you would have also available as default output in the graphical user interface. From the unsaturated zone module, it's the recharge that is really coming from the unsaturated zone to the saturated zone. Here you have the recharge that is coming from macro pore flow, and you have here also some feedback unsaturated zone recharge. But it is, in this case, ignoring the interaction with the rivers. So what we did, I can show you the example actually. we modified here, again, the default config file, where we have a total water balance, including the rivers and excluding the rivers. Oh, I think it's at the bottom. Here, yeah. And what you can see here is, now there are more items, simply written, typed with the keyboard. So next to the standard ones, we added also how much is coming from the overland flow to the saturated zone and vice versa, from the flooding, and also the river terms. And now I jump to the presentation. Yeah, here you can see it also in the presentation. We created this total recharge map including rivers and added these items here. And then we can create a nice groundwater recharge map on the left side, how you would see it per default output. And on the right side, you can see this dense river network, how it exfiltrates the groundwater. Now, what you would get here is, of course, again, the accumulated value to the very end. But if you divide this by the simulation period, you would get millimeters per day times 365. You get millimeters per year. And this you can really calculate. You can see here the unit in cubic meters per year. So, for example, if you would like to go for new water permits, if you plan to drill a new saturated zone well, you can create such a high resolution groundwater recharge map that directly shows you how much available water you would have for a new well permission, which is way more advanced than the most common GIS-based approaches. So you have here really clear on the left side what is recharged into the groundwater. But what you would miss on the left side is, of course, if you dig here somewhere a well, how much water is really available for a new well, because much of the water is already drained into the river. And this way you can, of course, tweak the water balance in a way like you want it or you need it, how you need it for your assessment. The last item for today is how to combine the water balance tool with the auto calibration tool, which is also quite nice. I mean, you know that this auto calibration tool for automated calibration can be used for detailed river and water movement time series, how I've shown you that in the how to build the MikeShe model 2 session. But there are also maybe outputs that are not available as time series, and AutoCal would need time series as target to calibrate your model automatically. But what you can do, if you create a new SHE file, I will not go through the AutoCal setup, so this is explained also in the second thing. If I click here on Edit, I can open the SHE file, and if some customized water balance configuration is attached to the SHE file here, it can create for you the time series on any random output that you want to have. In this case, this is a small use case example from Copenhagen University, who wanted to calibrate MikeShe for the throughfall. And this is part of the snow melt component. So what you can do here, let me show if I can open the water balance file. In this case, it was even not needed to change the default config file. They only needed to define here the snow melt component, which includes exactly this one single item that creates then here automatically a time series. And when AutoCal is running your SHE file, the water balance file will be executed at the end, and AutoCal is able to read exactly these outputs here that were created with the water balance tool. And then you can automatically calibrate your SHI file for certain items. You can also think, for example, that you make a sub-catchment grid code within your water balance file for your focus area, because you already know that the recharge will be around 250 millimeters per year. Then you can take this, create a dummy time series where everywhere you have 250 millimeters per year, and then insert for the model parameters, the unsaturated zone parameters or whatever, and then run the model in an automated way and simplify the calibration process for you a lot. I think that's mainly it for today. One side comment, if you are living in for example, in the US, it could be that it's not always written correctly in the water balance output file, but be sure that the output that is created by the water balance file is always normally in millimeters. If you are in the US and using US units, it will be inch. Yeah, for example, here 851. So this is always normally here in millimeter. And this should change to inch. Even if you have, maybe it is still written millimeter, I'm not sure. There was an issue in the past, but be sure if you're using US units, the unit here is inch. One last thing I think I forgot to mention is, now, for example, this model here, I took the carob example and I ran it for 3 years. Maybe I can open it quickly. Now let's assume you have a model that is running over many years. Now in this case, multiple years, 3 years here from 2001 to 2004. And you run your water balance file. You will see here, not a good example. Let me execute that one again. You see here pretty high numbers, like 2,500 millimeters. And at least we at DHI, or me, myself, we are thinking always in millimeters per year. So you always would like to see the average water balance of such an item. So what we did, and now you need to understand a little bit the structure, how this output looks like. I go again to the 3 years scenario, water balance. Okay, the correct timestamp. This is the one I created right now. That looks like that. Oh, sorry, that's the wrong one. Did not update. So it's really a simple text-based file. You can see here already the 2,500 millimeters. And what I will also share with you after the meeting is, don't get confused. We have an Excel sheet where we simply copy-paste the values, how they come from this produced output. I can do that now, of course. So I select everything. I press Control C, go in here, Control V. I overwrite the existing results like that, 2000. And here are some functions in there that read here this date string, convert it to a real date. Then it counts the number of days divided by 365, gives you the number of years. And then you have here, after the import file, several other sheets. For example, here, and this will create you the annually average. If you also do the effort to count the number of cells of your active model domain, and you type in here the cell resolution, it can calculate here the square meters, and it can recalculate the millimeters divided by 1000 times the catchment area in square meters to cubic meters per year, million cubic meters per year, and liters per second. So in this case, for this example, I show you here the averaged value. It's a little bit of clicking. I go now into my original file. I press Control A to select everything, Control V, exchange the numbers. I even have here a translation function in Excel. You would see it if you want. I open my chart output again, navigate to the correct folder here, and I have now the annual average. And you can see here a translation. You would see this yourself in the Excel sheet under headers. It is already prepared in a way that you can use the translation. That's the wrong one. Give me a second. Here it is. So we have the English version, German version, and this one. There is even a template where you can adjust this a little bit yourself. So we copy pasted here simply the diagram. If, for example, the letter size is too small for you, it refers here to the mean average value. You can do this as function. This you would have to change manually to your language, but this is also a way you can modify that. But we are working exactly on that. So we would like to improve this a little bit more, the representation in the near future. That's it for today. So thank you very much. I hope it was not too extensive. And here we have already the first question. Give me 1 second. I allow you the microphone. Fazli, now you can unmute yourself, please.
Hello, good afternoon. Can you hear me?
Yes, that works good.
Thanks a lot for the presentation. It was very nice and full of learning, as always. I have one question. Can we estimate the recharge from irrigation, from the irrigation command areas when it is flooded from the river?
No, I think not explicitly, because the problem is in MyXi, the irrigation works in a way that the irrigated amount is added to the precipitation. So you would have a MyXi topography cell, and in one time step you have some precipitation falling or not. Then the irrigation is added to that, and from there you cannot separate it anymore. But what you can do is, you can, of course, as I did it here, because we had the same question, I ran the model with and without irrigation, right? And then you can compare these ones. Or it's more easy for you probably to estimate it when you have no precipitation. And since I know your model area is in a very dry region of the world, you probably do not have too much precipitation maybe. So then it would be easy to distinguish a little bit. But I would say the easiest way is, again, to make one reference run with irrigation, turn off the irrigation, and see how the recharge changes.
Okay, the reason for asking this is that I want to analyze the impact of changing land use from agriculture to urban. So what would be the impact of that on the water balance? And I would be desperately waiting for the Excel files and also the configuration files I need for the water balance tool. So I would be looking for that. Kindly share it.
Yes, I will do. And we can also have a separate session on that. I know that you're quite motivated, so we can also see what works best for your model setup. Well, if you would like to change agriculture to urban, you would need to think what you want to change in terms of parameterization, right? So you would turn off the irrigation. You would probably change the leaf area index and the root depth to 0, but therefore you get sealed areas and more overland runoff. And you would need to implement this in your model. And then you would see exactly like that. I would recommend you to do this water balance analysis, right?
Yeah.
Which is pretty nice then to see the reference and the scenario and to compare it how the water balance changes. So this is one of the typical applications for MyXi to assess land use changes in the water balance.
Thanks a lot.
In the meantime, I answered the question from Kian. Thank you, Philip. This is a very helpful webinar. Could I ask if we have negative saturated zone storage change from the water balance calculation? How do we interpret it? Does this mean this aquifer is losing water and the aquifer is draining? Very good point, and it's a very tricky question, and it took me also some time to interpret that in the right way. Give me 1 second. I share again my screen. So going back to the English version. In this case, you see here the saturated zone storage change is minus 12 millimeter for the whole simulation period, which is in this case 1 year. This means, yes, the aquifer is kind of losing water. It's probably drained, or it's less recharge than outflows by the river. This would mean that in average, all groundwater heads in the model domain were falling after 1 year of simulation 12 millimeters. Amanda asks me, what parameters would you adjust to avoid negative saturated zone storage chains? Well, if you are in the calibration, you would not like to change it because it's part of the calibration. But if I rephrase the question a little bit, probably it's a dry year and it's reflecting realistic conditions. If you are already in the scenario analysis and you're running prediction runs, and your aquifer is running dry over many years and you would like to avoid that, then again, that's a good question and maybe a good showcase for this one. If I go back to this one, the first thing I would do such a water balance, focusing on the saturated zone on the groundwater. And then, yeah, okay, cool. I understand it the right way. Because from this chart output, you only know that your groundwater is drying out, but you don't know why. Is the recharge less? Is the green one too low? Or is the drainage too high, the yellow one? Or is the pumping increased? So this is exactly what you would do, right? You don't know why it's running dry, but you want to know why. If, for example, you have drainages, you can turn off drainages also in the reality, right? If you're talking about agricultural drainages, they can open and close the weir. If the rivers are like the base flow is too high, the rivers are draining too much, you could also implement weirs where you say, especially in the winter phase, or at least in Central Europe, when you have the recharging phase where you have low evapotranspiration, I want to keep back water. So this is probably the biggest market for us here in our project business. How to hold back, maintain the water in the groundwater. And what we normally do is we simulate with Mike Plus Rivers together coupled with Mike Shi, simulate several weir locations and then try to increase the water level in the rivers and therefore tweak the gradient, right? If you have higher river water levels, and you will drain less groundwater. Melinda, I ran into some microphone issues, no problem. In my case, the river cross-section is not maintained properly. Do you think having manually making the ideal conditions of river cross-section would make any difference in the groundwater recharge? That's a good question. Again, I would start with the water balance and see if really the river is the problem. I think we were already in contact also via email. Maybe we have a separate discussion on that because I'm not sure if I fully understand the question, especially the river cross-section is not maintained properly. But yes, if you define the groundwater recharge not only as the precipitation infiltrating and percolating downwards, then normally rivers are the main influencing factor of the real groundwater recharge. So the groundwater that is created newly within 1 year. Okay, we are already over time. I don't see any more. Yeah. Okay. Yes, the negative recharge, no problem. This means the aquifer is emptying. Yeah, it's running out. So in this case, you would have an average falling groundwater head of minus 12 millimeter for this simulation period. You can watch the recording. There you would have a more detailed explanation. So then I don't have to do it or repeat it because the others have seen it already. One last question, Fazli?
In this chart, we can't see pumping. Is the negative value the result of the excessive pumping?
No, in this case, there is no pumping. In this model, there I have no saturated zone wells. That's why exactly this item is hidden. So this recognizes already which modules are active and which not. In this case, it's really that we have simply this is maybe I don't know. This is the year 2001, which was a little bit more dry. That means compared to the previous average year, the precipitation was not enough compared to the saturated zone drainage that is happening, the natural base flow, and the evapotranspiration due to vegetation. So it's really a combination of in and outflow.
The unsaturated zone is also showing negative, and I have interpreted before this like if anything is adding to the system, that is negative, like precipitation and also recharge.
It depends on if you look at the raw text file. Yeah, there the sign convention is a little bit complicated, but if you look at this chart output, you see the correct items. So in this case, if you have USET storage, that means the soil was wetter at the beginning of the simulation, and it's a little bit drier, so the soil moisture content was decreased at the end of the simulation.
Okay.
Good.
Okay, thanks.
Yes, I will share all these Excel spreadsheets. I will step back from a more detailed explanation. I will share it with you. Try it yourself, test it a little bit, play around with it, and if you have questions, email me. Thank you very much. You will be provided with the documentation, with the PPT, the recorded webinar, and also the Excel sheets. Thank you very much. Have a nice day. See you next time. Bye.